Okay, hello, welcome back. There has been some confusion about the meaning of the word mobile in the title, so I figured that it would be a reminder that babies on their cribs, they have those little dangly star things, right? That's called a mobile. I'm not referring to one of these. I'm also not referring to babies in a car. That's kind of odd as well. That's what I'm referring to. And of course, the title of the talk is because quite famously, I'm not a parent, so I have no idea how true this is. These things can get all caught and tangled. And, well, if you're a smart baby, then hopefully you should be able to untangle it. So, okay, now that that's out of the way, I'd like to offer first my thanks to these 5 people, all of whom in some way helped me understand what a Taylor series is. Thank you. So, what is... Yes, okay, go away, little thing, so I can see my title. Thank you. What is knot theory all about? Well, knot theory, interestingly enough, I don't know how to move that thing, that's okay, is the study not necessarily of knots, but of links, which are knots of multiple strings in space. And I'm going to forget that I said that and just focus on proper knots, which are links of one strand in space. So that is, I take a strand in space, can tie it all up, maybe like this. I'm feeling a little bit lazy today. And that's what we study, right? Except we don't study these things. If you've never seen this before, this is just in case you haven't, because all these things are really stupid and boring, because what I can do is untie all of them. So to stop myself from doing that, the problem was that I pulled this end back through. All of our knots are linked together, joined together, glued together, whatever you want to say, at the end like that. And then suddenly this one can't be untied anymore. Okay, so... kind of the biggest central sort of problem in knot theory is how to tell when 2 knots are the same, and that's a whole big thing. Now, this talk is born out of a big frustration that I have, which is that all of the textbooks in this area are aimed at kindergartners and not at babies. Specifically, they do awesome things like saying that knots are piecewise linear or smooth curves in R3 or S3, which are related by ambient isotopies that are either piecewise linear or smooth, and give 0 examples of those and expect them to be self-evident. So that's pretty fun. And basically what I wanted to do here is kind of get the necessary little groundwork all nice and covered so that you can look at these things and not tear your eyes out, basically. Okay, so where we're going. The main goal of knot theory, as I said, is to tell knots apart, and that is really, 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 really hard. That is like several people in this room's entire job, pretty much. So instead, what we're going to do today is we're going to develop a tool for developing tools for telling knots apart. Now, specifically what I'm going to do is I'm going to tell you a little bedtime story, and I'm going to tell it from 2 perspectives. Excuse me. The first thing I'm going to do, if you remember how I said piecewise linear or smooth, I'm going to tell you the piecewise linear. And that's going to be the hero's journey, and we'll end up using some combinatorics. Then afterwards, we're going to turn to the story of the villain, which of course is the smooth perspective, and their analysis. Okay, so let's get started with the perspective of nice little polygons. So to capture this idea of a knot, nice and combinatorially, what I'm going to do is not have this wiggly strand. I'm going to have a piecewise linear simple closed curve in R3. That's my definition for a knot. So that's an example, and this took forever to make, so I'm never doing a 3D diagram again. And how do we tell whether 2 knots are the same? Well, sorry, how can we have actions that... Let me explain with this. Here's the thing, it's a knot, right? And if I do this, it's still the same knot, right? This motion through space we need to capture in our combinatorial setting, and we do it with these things called delta and delta inverse moves. So this whole long paragraph is to say the following. A delta move on a knot is what you get when you look at one edge of the knot, you draw out a triangle that does not intersect the knot. This little strand is kind of behind that triangle, if you will. And you replace this edge with those 2 edges of the triangle to get this. That is a delta move. A delta inverse move is that. Cool? Fantastic. Are we solved with those? Yes.
Can it be like collinear?
Yes, in fact, I am allowing degenerate triangles, which amounts to having the same picture in the end, except if you want the combinatorial data started with 2 vertices, and at the end, I've got an extra vertex that I'm able to add anywhere. Good question. Something in particular that I am ruling out is having triangles that self-intersect with the knot. If you want, the analogy there is that I have my strand, and I'm not allowed to pull it through itself. That's not how physics works, right? Okay. Cool. So that's the relationship that we're looking at. If we use these atomic moves and we take any sequence of those, we get what's known as an isotopy, and two knots are isotopic if they are related by one such sequence. So, for example, here's a knot that you've seen over and over. It's the ABC logo. And if I take a look at this, that's two edges of a triangle sitting behind this strand so that it doesn't self-intersect. I can do a delta inverse move there to get that. I can do another one and another one. And at this point, I can do one of those degenerate delta moves to alter the data to plot down an extra vertex there. And now I've got one side of a triangle, so I can do a delta move to get two sides and a delta inverse move. And hey, look, I've got a nice little, we're doing topology, so that's a circle, right? This knot and all the other ones that we just saw are called the unknot. Cool. So let me abuse the term knot now. A knot refers to either a curve as before or a class of them modulo this isotopy relation. And now that we're working in a quotient space, equality is hard to check, so the big question is how we tell knots apart. Okay. All right, so here's kind of the main tool that is cropped up. It's a knot invariant. A knot invariant, quite simply, is a function out of the set of knots modulo isotopy. In particular, being a function, if the outputs on two knots K1 and K2 are distinct, then these must actually be distinct knots K1 and K2, or knot isotopic, if you will. Cool. Awesome. Okay, so here's a couple of examples of knot invariants. The first is the unknotting number. If you think about those triangles and how they weren't allowed to pass through any of the knot when you did it, let's call one of those that actually does an illegal one, and the unknotting number, to be very, very loose and maybe not even technically precise, is the minimum number of these illegal moves to transform K into the unknot. The knot group is another one that I can tell you about. If I look at the image of my knot, that's some subset of R3. And what I do is I look at the complement, which is a whole bunch of space, and I take the fundamental group of that. That's another knot invariant, sure. But both of these kind of have a problem. The unknotting number, rather, would best be described as an export of knot theory, not a tool within. It would be really nice to know how many times I need to do illegal things to make this the unknot, and that might not really be all that easy to compute, or at least it certainly doesn't sound like it. In kind of a similar vein, the knot group turns the problem of recognizing knots into the problem of recognizing groups, which, yikes, that's a pretty bad problem too. So the question is how we can build nice invariants. Okay, so we're going to get to that, but first I'm going to take a little bit of a detour and I'm going to tell you about knot diagrams. So let pi be the projection from R3 down to R2. It is that projection, right? The image of our knot K under pi is said to be regular when the pre-image of any point on the plane lifts up and it meets at most two edges of K for any point on the plane. So in particular, something that I'm avoiding is here I've got three edges upstairs that will meet at a single point downstairs. If I lift that up, that's three upstairs, and no, that's not at most two. So no triple intersections, no quadruple intersections, and so on. Something else I'm forbidding, as a little bit of a cheeky special case, is if I have a vertex upstairs, and I project that down, and it happens to meet a line downstairs, well, down here, if I lift that up, I've got the line that it meets, and the two lines that are actually incident with the vertex. I am counting both of those two lines, so that this is a total of three, and is therefore forbidden. Yes?
Can you turn any of these knots into a regular one by computing these?
That's a very good question, and it is kind of the theme of the rest of the talk. So I will answer you, but I'll take a little bit. As an extension of this that we are also forbidding, if you imagine that I have two lines sitting upstairs and they happen to project to the same thing downstairs, this is not permissible as well. And the reason for that is even though there's only 2 points for most of this line downstairs, if I kind of start on those lines and I walk to the end of them, I'm going to meet a vertex of one of them while it's over the other line, and we just argued that we can't have vertices and lines in the same place downstairs. Cool. Okay, so that's a regular projection. Now, a knot diagram is what we get when we remember the information that some of these strands upstairs are over versus under the other ones. So here, kind of like everyone draws cubes with their little lines that break when they go behind others, that's how I'm going to draw them And that's how I'm drawing my knot diagrams. Cool. All right. So I promise you that every knot has many diagrams, and in particular, if you have one that's not, it is possible to perturb it in an arbitrarily small way to make one. And we will kind of return to this later. Okay, so now a question. Upstairs, we had delta moves that were able to replace knots, edges with other ones and get from knots to other knots. These should, well, I guess the question is, like, what do these look like downstairs? These should give us ways to relate diagrams to one another. The first thing that can happen is a delta 1 move. A delta 1 move on a diagram is simply a delta move. There's just a different name for the same thing to emphasize the fact that we're downstairs now. So these don't intersect any extra part of the diagram downstairs. Do we need a visual example of this? No, cool. What's more interesting is a delta 2 move, which, oh, yikes. A delta 2 move is what happens when I have an edge and a triangle that I'm going to be moving downstairs. And if we have a look at the triangle, it is cut by another edge of the knot, which meets UW in exactly 1 point, and it meets VW in exactly 1 point, neither of which is the corner. And we're allowed to do this replacement. We call it a delta 2 move, replacing UW with UV and VW. The effect of this, and something I want to impress at the moment, is that if you imagine kind of taking this and kind of dragging this up until it becomes these two, then along that whole process, this crossing will get moved over to here. So you should see this as just pulling a strand and the crossing moving along. Cool? Yes?
If we have a triangle with base U to W, is there any points that would be an illegal move for that third point in that triangle? Like, can we move V around anywhere we would like and it would still be a delta 2 move?
I am not allowed to put it here, for example,
Okay.
because then the result that I get is not a diagram. And I guess that's something I should have spelled out a bit more, but does that make sense? Cool. Otherwise, all good? Fantastic. Okay, so those two, together with the inverse operations, going from the two edges back to the one edge of the triangle, are our delta I and delta I inverse moves. Two diagrams are said to be isotopic if they are related by a sequence of these moves. Cool? All right. Now, what's kind of, oh yes?
Do we know that every delta move is one of these two moves in 3D space down to?
Good question. You are also hitting on the remainder of this half of the talk. And the answer to that is no, and we are going to see that they give rise to Reidemeister moves. Okay, so a question, can we use diagrams to define knot invariance? The answer is yes. Here's a kind of meh one. The crossing number of k is the minimum number of crossings among all diagrams of k. And why it's kind of meh is that you have to consider the infinitude of all possible diagrams, and then that doesn't sound particularly easy to have a look at. What's less meh about it is that the standard knot tables are ordered first by the crossing number, so it's at least somewhat useful in the real world. Yes?
Forgive me, but
Yes?
as it stands with the current moves that we're given, do we have any way to eliminate a crossing in our diagrams?
No.
No, okay.
Yeah.
So then how can we define this invariant?
You might have,
Oh,
so,
we can take different projections.
yes.
I see, okay.
And in more to the point, a diagram upstairs, sorry, a knot upstairs, I should say. Let me unlink this one. A knot upstairs, this one has the very trivial diagram. This diagram has one crossing, but they're the same knot, and I have to consider both diagrams when I'm computing the unknotting number.
So this is the event of the knot diagram.
Yes. Exactly. What we're seeing here is that this is not computable from any particular diagram, and that's what makes it very hard to work with, right? So a better question is whether we can define invariants that are computable for any particular diagram. And to hit on this, I want to introduce what are known as the Reidemeister moves. So on a diagram, pi, so projection of a knot, an omega-1 Reidemeister move is the image of a delta move upstairs that turns a path that contains no double points downstairs into one that contains a loop. And here is that loop in the example. Okay? That's an omega-1 move. Now, an omega-2 move is something that gets a much longer paragraph to describe formally, and I'm going to be a little bit lazy and say that it's the image of a delta move upstairs that pulls one path over another. So, pulled over, right? And let me be similarly lazy to define an omega-3 move, which is what I get when I pull one path over a crossing. So those are your three Reidemeister moves, omega-1, omega-2, and omega-3. Them, together with their reverses, I guess, are called the Reidemeister moves. And it is a very famous theorem that knots modular isotopy are in bijective correspondence to their diagrams modular, not just isotopy, but you also have to permit the Reidemeister moves. Now, let me give you the original phrasing of this. The original phrasing by Reidemeister was some German, and that translates to the following. Any property of knots modular isotopy coincides with those properties of diagrams modular isotopy which are preserved under the Reidemeister moves. Except he also didn't use the word Reidemeister because that would be him talking about himself. So, yes. What's kind of cheeky about this, and I had a little smile to myself, is that he was using the unite lemma before the train left the station. Anyway. Okay, a consequence of this. Any function defined on diagrams is a knot invariant just when its values are unchanged by diagram isotopy, which will happen most of the time, and the Reidemeister moves. Those are the big ones to check. In particular, one can construct this thing called the Jones polynomial. I'm not going to tell you very much about it, but I can point and say, oh, look, links. That we glossed over those earlier. And it's an invariant. It can be computed recursively given a diagram. This one, also, by the way, is an actually good invariant, unlike the other ones that we've said on the list. Okay. Good for a definition of a baby. Neat. You can use this, for example, to prove that the unknot is different to the trifoil, for example. Okay. So let's turn to proving Reidemeister's theorem. So first things first, we want to say that if we have two equal knots, so that is two curves that differ by isotopy, then we can recreate down in the level of diagrams the difference between the diagrams as a sequence of these delta I and omega I moves. So that's very easy because by definition they were all images of delta moves upstairs, right? So, no, that's not what I want to say. Sorry. Let me restart that. If I have two diagrams that are the same up to delta I's and omega I's downstairs, that's what I want to say, sorry, then the two knots that they came from must be isotopic. And that's very easy because by definition, each of these Reidemeister moves lifts to one of these delta moves upstairs, so you get a sequence of them. Wow, fantastic. So let me prove the thing that I said the other way around. If we start with two knots upstairs that are related by a sequence of isotopies, can we get downstairs a sequence of these moves? Yes?
It is true that these moves lift to these other moves in that ambient space, but they're not unique. There's a butt ton of them.
Sure.
So how do we know that the sequence that we took up would work?
Yeah, good question. The way that I'm defining them, they are precisely the images of these. That is kind of slightly glossing over something where you could say I could consider these pictures on their own and do them. That is something that I'm choosing not to look at, partially because I have that long left and partially because I don't want to. So,
It's not true that it is still.
it is still true. Okay, so first things first, going back from having two isotopic knots trying to get to Reidemeister moves downstairs, the very first thing we're going to do in this proof is we're going to start being lazy. So rather than having a knot literally be a bunch of piecewise linear tiny little segments, I want you to make those segments so tiny that we can forgive ourselves for drawing smooth little curves downstairs. And those delta moves, I want you to have them so tiny that we can forgive ourselves by viewing them as little wigglings of our curves around. So let's start being lazy. For example, these three strands, I can wiggle them over to make them look like this, right? And in particular, something that's actually critical is that the information of these crossings is completely preserved. Neat. Okay, so here's what the Reidemeister moves look like in this lazy setting. Here, this is what the omega-1 moves looks like. It kind of looks like untwisting a curl. And omega-2, looks like having strands pass over each other, but the picture's a little bit more symmetric now, which is kind of nice. And likewise, I can make a more symmetric looking omega-3 picture. Yes.
Are these diagrams knots?
Yeah, so sorry. These diagrams are little snippets of knots. So I want you to imagine the rest of a knot coming out here, and I focus on a particular crossing where I apply these moves, or a particular little segment. That's what the dotted outline was supposed to convey. Yeah. Does that make sense? Fantastic. Okay. All right, so now that we've got this, well, one could feasibly think, okay, well, this is the omega-1 where the strand coming from above goes under and then it comes over. What if we had an over one and then it became an under strand, a different version of one of these moves? And you can do this for all of them. You can consider these different versions. It turns out that the 3 vanilla Reidemeister moves are enough to get back to all of them. For example, this one where I had the opposite sort of over-under for this omega-1 crossing, I can do a real omega-1 over here, and then I get this kind of 2 overlinked strands, sorry, 1 strand over another sort of configuration, which I can undo with the Reidemeister 2 move, and isotopy is enough to get it back to a nice straight segment. So all of these versions, I promise you it's more of an exercise than anything, is to just get all of these from the original omega I. Okay, so this granted, what we're going to do is we're going to be lazy enough to not even mention these delta i's, the diagram isotopies, and we're going to just squash all of these Reidemeister versions and call them all omega-1, omega-2, omega-3. Cool? Okay. So at this point, it's enough now to recreate the effect of an arbitrary delta move upstairs by Reidemeister moves downstairs. Cool. So the problem is that an arbitrary move upstairs may be rather complicated downstairs. It might cross over multiple crossings, extra bits that don't actually have crossings in the middle, might cross over vertices, and so on and so forth. So what we're going to do is, because this is nice and combinatorial, we've got a finite number of these little segments to actually consider, I'm going to chop up this triangle. So we're going to triangulate it in a way that isolates each of these interesting interactions one by one, so there's only one thing to consider in each triangle. Now, if I've done that, I can move from this pink edge. My goal is to move from the pink edge to the blue edge, by the way. I can move from this pink edge to these 2 here. After that, I can move from here to these 2 here, and so on and so forth, until I have migrated the pink edge down to cover the blue one. Yes?
Why must we find the many extensions?
Well, there are finitely many vertices, and there are finitely many crossings, because there are finitely many strands upstairs.
Is that
Finitely many edges upstairs. Yes, by definition, it's a piecewise linear curve. Yeah. Yes?
Is there a way to specifically create a triangulation?
Yes, so I should tell you the rules for it. I think it's kind of self-evident enough. The way that Reidemeister justifies it is to cut parallel to this and parallel to this edge up here. And because there's only finitely many things to avoid, there's space in between. Oh yeah. Okay, so here's the rules for how I'm going to make my crossings. I'm only going to allow these 5, technically 6 interactions. The first thing is a mini triangle downstairs may have absolutely nothing else from the knot intersecting it. I'm cool with that. It may also have a single edge that cuts through with no crossing, no vertex, no nothing in the middle, just passing through. We may bump that up to have a single vertex inside and the 2 edges incident, or a single crossing inside and the 2 edges that participate in that. That's enough for most of them. The only technicality is that I may have vertices, in fact I do have vertices rather, on the endpoints of my original edge UW that I'm trying to replace. So I'm going to allow 2 special triangles, or 2 special triangle types. One of them deals with this case where the extra edge that's not UW incident with that vertex goes outside the triangle. That's cool. The other one is where it goes into the triangle. That's cool. I'm not allowing it to be perpendicular, like along the same edge of the triangle is what I'm getting at. Okay, so those are the 5, technically 6 interactions I'm allowing. Some things that I'm ruling out in particular are an edge that cuts through the corner of a triangle, like this or like that, and I'm not permitting a vertex to lie on the corner of a triangle either, for example, except for those special edge cases. Okay, I think it's sufficiently obvious that this can be done. Cool. Okay, so then, now that we've got these cases, let's enumerate all the interactions. These are what they look like. These are all the interactions. We can have nothing going on. We can have an edge which passes through the incoming pink and goes out to where we're trying to get to, the blue. We can have one that passes through both the blue but doesn't touch the pink, and so on and so forth. Now what's very nice here is that the moves that we want to do on these, most of them are things we've already seen. That's a delta 1 move, nothing special going on. That one's a delta 2 move. That was an omega 2 move because I'm taking this pink and I'm passing it over or under the white. This one is a delta 1. This is the only instance in the proof of an omega 1, and I can keep labeling. A bunch of these are omega 2s, these two are omega 3s, but these two unfortunately are not. And to see that, if you have a look at one of these, there's a crossing, a crossing, a crossing. In our original version that has the pink edge, 3 mutually adjacent crossings is the kind of situation you need to start an omega 3 move. Over here, we don't have 3 crossings at all, let alone mutually adjacent ones, and the situation's even worse over here where there's absolutely nothing touching the pink edge. So I've got those 2 cases left to do. So what's really neat is that I can reduce one to the other. If I start with this, one can imagine taking this triangle and rotating it and moving it nice and smaller, and if you do that, you can get it to a point where the pink edge doesn't touch these white ones at all. And then if you tilt your head and squint a bit, you'll notice that we're looking at this again. If you're not totally convinced by that, here's a triangulation that you can get over in delta 1 and delta 2 moves. So we have one case left to do. And that one, fortunately, is rather straightforward. We start with this edge. We use an omega 2 move to pull it up to here. We drop down an extra vertex and then do another move to pull that up into here. And now I've got 3 mutually adjacent ones, which I can undo with an omega 3. And that's the conclusion of our case analysis, and the end of the hero's journey. Cool. So now it's time for the villain, which, of course, if the hero was combinatorics, the villain is definitely analysis. So, okay, a leading question that I want to start with. The very first thing we did in that proof is we said, let's not work with straight things. Let's allow ourselves to be wibbly-wobbly and then wibble-wobble the wibble-wobbles, right? And when we start waving our hands like this, that's how we know we're doing topology. So the natural question is whether we can work with continuous curves instead. And the answer to this is, unfortunately, not quite. A candidate definition is that a knot would be a homeomorphism of S1 onto some subset of R3. And this does not capture the same thing as before. Here is a knot that Fox calls remarkable, and also that Kroll and Fox call remarkable. I've only seen Fox call it remarkable, but anyway. And what we have is this situation where I've got a strand where I could pull it back to undo this. That would unlock this strand, which I can pull back to unlock this strand. And I can nest these, going arbitrarily small, and have infinitely many of them. And okay, well, that's something that I can do, sure. What's interesting about this is that this diagram has infinitely many crossings. That is certainly not something that we can make with our piecewise linear things. And furthermore, there is a sequence, granted an infinite one, that undoes all of the crossings, yet it doesn't undo the whole knot. Yes?
So in the polygon case, was there some condition that I forgot about, only finitely many?
There are only finitely many edges, yes. Yep.
So by piecewise linear, do you mean trivializable?
I mean,
Exponential.
Finitely many sticks.
yeah.
So I mean, doesn't imply finite many.
I am specifically requiring it to be finitely many.
Okay.
It was my impression that this was part of the definition, but if not, tack it on to part of the definition.
Maybe this, so that's a homeomorphism of the sphere.
Supposedly, I haven't checked, but yeah, it's quite weird. But yeah. The takeaway from this is that we need to focus on a more restricted class. Let's call them tame knots. So rather than just working continuously, what we're going to do is we're going to get really evil and work smooth. This statement that I've just heard, that there's no real nice path to defining invariants that are sensible and computable for these really wild sort of things, is another motivation for focusing on tame knots, because we can actually do something with them. Okay, so our real definition. A tame knot is going to be a smooth injection of the circle into R3. Okay, now let me start retelling the story. We had our isotopies to move between knots, and I'm going to kind of blitz this a little bit and then give you intuition afterwards. An ambient isotopy on a manifold Y is a smooth map from Y across the interval to Y with the property that this map is a diffeomorphism of Y cross I. Yikes, but something I can do with those is if I have two knots from S1 into R3, then I'm going to say that they're ambient isotopic when there is an ambient isotopy that at time 0, or think of the interval parameter as being time, is the identity transformation, and at time 1 it moves F onto G. Okay, and then let me abuse language again. A knot is either a curve or a class of them modulo ambient isotopy. Let me give you a couple impressions of these. So first, these are all smooth knots. Yeah. These two I've shown you a couple times. This one I have tied on my wallet. Okay. Let me give you an impression for ambient isotopy now. And what I want to impress upon you is that it is an incredibly malleable thing. These are incredibly general relationships. So first, isotopies can be global. If you think of doing a rotation, here I've got it by 1/3 of a full turn, you could think of the before and after as two discrete things, or you could think of the whole continuum of small rotations in between. That is an ambient isotopy, so we see that they can affect global change. Now, to make this picture a bit clearer, this analogy of like a little YouTube play bar, and then you've got pictures for different phases of the video, I'm going to be using that analogy the whole way through, so let's stick with that. Okay, so isotopies can be global. What's kind of insane is that they can also be local. So if I have a small neighborhood, let me just cut out a disk from the plane, and I have a point of interest, I can imagine dragging that point to the center. And if I do that, you can think of emanating lines out of it to meet points on the boundary, and those lines get dragged along as well, which drags all the points inside this disk until I have moved that point to the center, that point of interest P to the center. Outside, I can choose to just not do anything at all, leave them alone. So isotopies give us a way to also affect local change with this sort of strategy and others like it. Something that's actually quite cool with that, excuse me, something that's quite cool with that is that you can use this idea, push it a bit further, and if you have a bunch of things that meet, if you have a curve that meets a bunch of these disks in only one point per disk, then you can use this sort of strategy on each disk and stitch them together, long sentence, to take one of these curves and flatten it into a line. And this is where we're starting to see that this sort of smooth idea and this PL, piecewise linear idea from before, are kind of the same. If you want more details, you can see Appendix I of Crowell and Fox. Okay, so what was the next step in our story? Knot diagrams. Well, what is a knot diagram? If I have a knot and then the projection, I'm going to say that their composite is a knot diagram just when the following 3 conditions hold. Number 3, any multiple points, that is points with pre-image more than 1, they have to be double points. Pre-image is exactly 2 points. All these double points must intersect transversely. What I mean by that is that the intersections, I think black will look better, look like this. In particular, they do not look like this, and they just kind of scapegoat being a crossover. So every one of these looks like a crossover, essentially. And last but not least, I'm not allowing cusps. No. And that's the only time I'll use the whiteboard, so it's okay to be messy. Okay, so those are our 3 conditions. Now let me remind you of the Reidemeister moves. Oh, sorry, remark, 2 knot diagrams can be isotopic as well. We had a general definition of ambient isotopy applied in the plane. Cool. So let me remind you of the 3 Reidemeister moves. This is what the omega-3 looks like, the omega-2 and the omega-1. I want you to imagine having this strand upstairs, and the move is kind of to just drag the strand until it goes under. At some critical point in time, it will cut right over the crossing and will be a triple point, violating that condition. And if you look at the omega-2 move, as you go back and back, at some point, we will have a non-transverse intersection, violating that condition. And if you look at what untwisting that little twist upstairs looks like, if you look at that in the projection, you will get a cusp for a brief moment in time that violates that condition. And so in this framework, these 3 conditions for being a knot diagram kind of inform exactly what the 3 Reidemeister moves need to be. Although I have motivated this by going backwards, the whole charge for the rest of the talk is to show you that you can go the other way too. All right, so let me remind you, the big theorem is that knots modulo ambient isotopy are the same as knot diagrams modulo isotopy in the Reidemeister moves. The big technique here, and I'm following a note on the archive by Holkeflik, is multi-jet transversality. Now, those are some big words. Let me kind of sort of get to them. So, a definition, two submanifolds of X are transverse just when the, well, where is it? Tangent space at X decomposes as the direct sum of the tangent spaces of my two submanifolds. In the case of two curves, the plane is made up by this and that. And they're different directions. So in particular, this sort of thing linearly looks like this, which doesn't even span the plane, let alone being a direct sum either, which it's not. So that's kind of neat. And the requirement is that is true of every point in the intersection. Now, some things we can read off of this. If the intersection is empty, vacuously they are transverse. If the dimension of V is less than the codimension of W and they are transverse, well, if we look at the condition, the codimension of W is how many more dimensions I need to tack onto this to get back all of this tangent space. And the condition is that V doesn't provide enough. So this equation can never be satisfied, and therefore we must have no points in the intersection. So if dim V is less than codim W and they are transverse, the intersection is empty. Now, in the other extreme sort of case, where the dimension and the codimension match and they are transverse, it turns out that the intersect W is a manifold, and if you count up the right dimension for it, it has to be a zero-dimensional manifold, so countably many discrete points. Nice. Okay, let me tell you very, very loosely about multijets. So, okay, yuck. The n-fold k-jet bundle from x to y describes the possible behaviors up to order k of smooth functions from x to y at n tuples of distinct points in x. And that's a bit of a mouthful. If it washes over you, don't be worried. A further loose definition, if I have a particular smooth map, I can have this thing called jknf. What it does is it sends such n tuples of distinct points to the kth order behaviors of f at those points. Again, I'm being very, very loose. I'm also going to call the image of one of these guys the graph of f and denote it by graph of f. So, for example, if f goes from R1 to R3, and I look at J01 of f, what this is one input point, and I'm looking at the output behavior up to order 0. So if I collect all those together in a set, one input point, just the output behavior up to order 0, I have literally the graph of f. That's why it's called graph of f in all these other cases. Now, to give you an impression of what else I can do with this, if I have 3 input points and I'm looking up to first order, then what this looks like is I collect together 3 tuples with an input point, the output, and the first order information at the output, so the value of the derivative. Okay, let me show you what can be done with these instead. So, let W be a submanifold of J02 from S1 to R3. So the points in them are 2 input points, let me call them theta1 and theta2, coming from S1. And we're going up to 0th order in the output. So just the output points, P1 and P2. The condition I'm going to prescribe is that these have to be distinct input points. Well, I can't highlight. These have to be distinct input points, but also the outputs are requiring to be equal. Now, what's interesting about this is I can ask what the graph of f intersect W looks like, and it looks like tuples as before with this condition, just that the output points are f of the input points. And okay, let me simplify the data a little bit because these are determined by those. So it looks like 2 points, theta1 and theta2, which are distinct, but whose images are equal. Okay. So that is to say, points of this intersection are failures of injectivity for our function. Now, let me tell you a big, heavy theorem. If W is a submanifold of one of these jkn's, then the set of functions, smooth functions from x to y, with graphs transverse to W, is dense in the space of smooth functions. To be extremely lazy, I can say that a generic smooth map has a graph transverse to W. So returning to our example, points of this intersection describe failures of injectivity. For generic f, this graph and submanifold are transverse. The dimension of the graph, it's controlled by 2 one-dimensional parameters, dimension 2. The codimension of the manifold, we impose 3-dimensional output to be 3-dimensional output, codimension 3. These are too far apart for there to be anything in the intersection, so the intersection is empty, which is to say that f is injective. What we have seen is that a generic function, a generic smooth map, is injective, i.e. it is a knot. At least a generic one from S1 to R3, I should be specific. Okay. Now, you can do a little bit of a similar sort of song and dance. You can conclude that the projection of a knot is generically a knot diagram as well. That is, that it satisfies those three conditions. Okay, now what I want to do is I want to kind of recover the Reidemeister moves in this framework. And let me call this an argument rather than a full proof. I haven't convinced myself of the very, very technical details of this, so let me at least call it just an argument. So, what we're going to do is we're going to have a look at the composite of a starting knot with an ambient isotopy that gives me a map from S1 across the interval into R3. And I'm going to analyze what happens to conditions 3, 2, and 1. So first, condition 3 was that the only multiple points are double points. I can write down this particular submanifold, and what it says is, give me 3 input points. Let me look at their outputs up to order 0. What I'm going to do with those outputs is say that I'm looking at a common time, and that I'm looking at a common point in the projected diagram. Okay, well, I can ask the same question. A generic graph. Yes. If I have a generic graph, I know that it will be transverse to this guy. So let me count dimension and codimension again. Graph of f has dimension 6. W has codimension 6. So the intersection is a 0 manifold. And because the domain I'm working with is compact, furthermore, that has to consist of finitely many points. Okay. So elements of this intersection as well describe triple or higher points. That was the whole construction. So points in the output that project to the same. Okay. So this is what we have. Finitely many more than double points. Let me pull the wool over your eyes a bit and change up the manifold. I'm now having 4 input points. And if I do that, then I have one more constraint here, 1 dimension, and I have an extra 2 dimensions. So the codimension is bumped up by 3. Meanwhile, the dimension of the graph, it takes 1 more 2-dimensional input, so the graph dimension only goes up by 2, and so that is too small to make up for the 3 extra in the codimension. So generically, this doesn't happen. We don't have quadruple or higher points. So for a generic f, we have finitely many more than double points, all of which are triple points. I can pull the wool over your eyes again. I can start adding first order information, and I can write down that the first derivatives are collinear, and generically that won't happen again. You can count dimension and codimension. So generically, the theta tangents point in different directions, and a similar thing with the t derivatives. They also point in different directions. Okay, so I have triple points where the theta tangents point in different directions, and the t derivatives point in different directions. Let me draw that for you. And what I'm drawing here is I'm at the common time, and I'm going to have a look at a little offset delta. Start with delta is 0. I'm going to draw these curves out in a little epsilon neighborhood of the theta I. Okay, so if I do that, this is what I get. 3 things intersect at a common point, different tangent directions, and different directions in which that point of interest is going to move, different time derivatives. If I play that forward in time, well, I'll have that these 3 strands move away at different rates. So I'm going to open up 3 mutually adjacent crossings. Kind of interesting. And if I play it backward in time, the same thing happens, but in reverse. 3 mutually adjacent crossings, but on the other side. If you compare before and after, this is the 3-strand Reidemeister move. Nice. For the condition 2, we can do this whole same song and dance again. This is the right submanifold to look at. The intersection is finite, describing non-transverse double points. These are not secretly triple or higher points. You would change up the manifold again, analyze dimension and codimension. And the time derivatives are not collinear, and the curvatures are different. If we draw that, this is what we get. A double point that is not secretly a triple or higher, different curvatures, moving in different ways, in different directions, sorry. Before and after, looks like a Reidemeister 2 move. And look, you can do the whole song and dance for number 1 as well. This is the thing to write down. These describe cusps that are not multiple points. Change up the manifold again. The correct thing to make the following picture make sense is not 0. And if you draw it, you get something that looks like this. A cusp. And if you move forward in time, it looks like a twist. And if you move backwards, it looks like a smoothing. That's the omega 1 move. So there we go. We have these at finitely many points in time, and in between it must be just an isotopy. That's Reidemeister's theorem. So there's at least a kind of smooth argument for it. And if you don't believe it, that's because analysis is evil. So let's move on. So great. In my last little bit, we've read both sides of the book. Let me now close it up. So what we've seen is that piecewise linear injective curves from S1 into R3 are the same as diagrams. Modular Reidemeister moves are the same as smooth versions of these curves. One can ask whether there's a direct connection from here to here instead of going via diagrams, and there is. You can read Appendix I of chronologics. Okay, let me summarize. Knots are piecewise linear or smooth injections of S1 into R3. Knots are the same when they are isotopic for either definition of isotopy. Knot invariants tell knots apart, but useful ones can be quite hard to define. Knots have diagrams, which themselves may be isotopic, and the big result is that diagrams modular isotopy and the Reidemeister moves are the same as knots themselves modular isotopy. This sort of framework lets us define knot invariants that are actually computable using the discrete data in a knot diagram, and using the Reidemeister moves, or rather checking against the Reidemeister moves, we can verify that these don't actually depend on the particular representative diagram for our knot. So that's all I have for you today. Here are my references, and thank you for listening.